Alright, my name is Ryan Smith, and I'm a master's student at Mississippi State University. And today I'm going to talk about the aggregation of Choquet integrals in GPR and EMI for handheld platform-based explosive hazard detection. Our approach is we were given the EMI and GPR data. So we then feed these data sets through our pre-screeners. So we have two pre-screeners for the GPR data that were previously developed by MSU. We have the curvelet-based approach and then the background adaptive approach. For the EMI data set we ran ACE. This algorithm was developed by the University of Missouri. And so these pre-screeners are going to give us discrete hit locations along with a confidence value they're coming back from these. And our specific work is going to start in the registration, resampling, and normalization. From that step, we're going to actually look at the fusion of these EMI and GPR sensors to get better detections. And then we're going to go look at scoring with some FARs. Alright, so registration to start off with. This is just an example of maybe a GPR scanning of the surface. So we'll have our northings and eastings. This is what we're looking at, and these dotted lines are the pattern, the sweeping pattern from the GPR. And this little dot in the center would represent the GPR sensor location, and the circles would be the field of view of the sensor. So that's just an example of the first GPR. And then the second one will be our EMI sensor. We'll have the same thing. We'll have this sweeping pattern. But we're going to run into a problem with the sweeping patterns because they were collected independently, and when we put them and overlay them, you'll see that the fields of view don't exactly align, and the locations of what they were collected don't align as well. So what we're going to look for, is what we're trying to do, is link these together. And we'll do that by taking the common area you see in purple, and then we're going to regularly sample this grid. And from the location, or from the confidence value from the pre-screener that we get these locations, and then we're going to have to go back and propagate our confidence values onto this grid that we've made. So we'll propagate per algorithm onto our sampling grid, giving us a one-to-one mapping for the algorithms for us to compare. Alright, so the resampling methods we use, we start from trivial resampling from the closest all the way down to some more complex and sophisticated with some spline interpolations. And we'll start with the closest. It's simple. We'll take from the discrete hit list, we'll go to the map, or the regularly sampled grid we created. And we'll just say, what is the closest point from one of our target locations returned from the pre-screener. So this is going to create a highly sparse map. The next one we'll go over is the nearest neighbor. So what this will do is kind of the inverse of that. We'll go from the map, or the regularly sampled grid, to the discrete points. And this is kind of, in a way, kind of bad if you think about it. If a point were, say, 2 or 3 meters away, and it was the closest point, it will get assigned. So we're going to get some inflation with this technique. To kind of mitigate that, we'll do a bounded nearest neighbor. We'll say, hey, try to incorporate maybe the field of view of your sensor, and we'll, go back. And say bound it so it doesn't propagate too far. And then we'll do another technique where we'll say, within this area, we'll take the max of the confidence value that was returned. The next resampling technique we'll go through is the Gaussian. And this is where we'll take each of the discrete points that we have, and we'll just put a Gaussian halo around. Right? And that Gaussian halo can be interpreted different ways. So we'll have the sigma that governs the halo, and that can be interpreted as your field of view of the sensor, or since we're returning confidence values from the pre-screener, it can be like alarm decay. So like we're real confident at the peak of the Gaussian, but as we go out, we're not as confident as a hit location. And the next one we're going to do is the splines. So we did, like I said, we have a discrete set of points, so we can interpolate a function to do our surface creation here. And we have different types of splines. We have the discontinuous, the linear splines, and then we'll get to the cubic and bicubic. But as we go in higher order, our computational costs, or you take those into account. Alright, so this is just an example of some of the maps that we created with our GPR. At the top, you'll see the closest. Like I said before, this blue region here will be the sparse, or it's showing the sparsity of this. So these are 0; they were never assigned. And then we'll see the little blips here where the confidence values were. The Gaussian is just where we took each individual SPIE location and we put a Gaussian halo around it. And then the spline technique here at the bottom. Noticed some problems with the spline technique because of overinflation. So this is just we have no, well, yeah, we're creating this line across here because we don't have anything in this between these hits to say, hey, you know, you need to guide the curve down. And we mitigated that by grounding these points on the map. So before, we were getting the ungrounded point where we were getting this overflated region. So now we'll go back into our map and actually hard-code 0 values so we have some guided points for the splines to go down. And this is just another 2D example of what it would look like for the overinflation and then when we ground it. So we'll actually go in and insert points with the red dots. All right. So here's just another example of showing the grounded spline interpolation. So with the Gaussian on the EMI data, so the EMI data did really well on this lane, or these sets of lanes. So we have really sparse data. And you can see the effects of regular splines without the grounded, and it gets super inflated, and we're trying to mitigate that. So we grounded it, and we'll get our surface that looks like this. Now, I don't know if it's hard to see at the top up here. I'm not sure if y'all can see this, but there are 2 false alarms up here that at the halo, or for the Gaussian, just gets the halos put around them. And they look like 2 little stack Gaussian points. But in the grounded spline, we're actually able to link them. So there are some advantages of having our grounded spline. Alright, so now that we have a way to populate our map, what we're looking at here is just a regular color image where I've put the EMI data in the red channel, the GPR in the green, and the ground truth in the blue. So what all this means is wherever you see white points is where both sensors, EMI and the GPR, were able to detect the target. And what we'll see in purple is where only the EMI, and blue is only the GPR. So we know off the bat now that if we have both of these sensors, that we can increase our detection rate. So we can go further in a little bit. The red channels or red dots are where the EMI is a false alarm, and then the green is where the GPR is a false alarm. And of course we have the yellow dots where it's just both EMI and GPR got it wrong. Alright. So now that we have, we know fusion is possible, we need a branch of mathematics that we can use to help us fuse together. So we chose the Choquet integral, which integrates over our partial support function h, which is our sensor inputs, and it's accompanied by this W sub I, which is this capacity, is this notion of our aggregation philosophy. This fuzzy measure, this fuzzy measure capacity can range from optimistic to pessimistic, like aggregation strategies. So the first kind of aggregation strategy for the Choquet is the one-size-fits-all type fusion philosophy. So we're saying, you know, you can take just the max value return from all of these, and then we're going to get a little more complex later, and we'll say, well, maybe you need different fusion strategies within sensor sets. So maybe our 2 GPR sensors need a intersection-like aggregation, and our 2 EMI sensors need a union-like, and then we can take the expected value. So we're trying to encode different aggregation philosophies and tailor them to different sensors outputs. So, and then in the end, again, we can take it a step further, and then we can do the composition and combinations of CHIs. So our preliminary experiments where we had our 2 platforms, and they were independently collected, and we ran our 2 GPR algorithms, our curvelets with our BAD, in conjunction with the 2 EMI sensors, or two EMI, our EMI algorithm from the University of Missouri, which was ACE, and then the difference between the two sets were one ACE with connected components and the other one was ran with mean shift for linking. We had 6 runs and 70 targets, and then once each one of these fusion trees were ran, we get one of the maps that I showed you earlier, and we use a simple extrema finder to find the peaks. Alright, so here's just first of our results here, showing that the fusion is useful. So like I said before, the EMI did really well on these lanes, so we want to see if the fusion is at least gives us some type of gain with respect to one sensor. So you can see the red is this EMI times the Choquet interval of an EMI and a GPR. You can see over at the top that it's outperforming the EMI, and then as we run it out to the run the far out, we can actually get 100% protection. So this gives us a little ground basis for us to look a little further. Alright, so for these experiments, we're going to look at a wide variety of Choquet intervals. So here we go. This is just a zoomed in picture, so we're going to look at, this is our EMI only, you can see at the top, and our GPR. So first I talked about just single Choquet intervals, where it was a one-size-fits-all type philosophy. And you can see where, in the red line, it's pointing to where our EMI only algorithm, and then we could see that the single Choquets really weren't giving us much of performance, if not that, like, a little bit better or on par with EMI by itself. So, and then we move on to our other aggregation strategies where we can tailor them a little bit more, and we'll start to see some performance increase in terms. So we know that now that the Choquet and tailoring actually does help. So from here we'll take our best example, or our best result that we have, and then we're going to go look at some the impacts of resampling, as we talked about each of the ways that we did our resampling. So we'll look at here. What was an interesting find here is that the closest actually did better. We didn't expect that, but it did turn out that way. And these other techniques, such as the bounded nearest neighbor and the nearest neighbor, where we tried to incorporate field of view, we fell here. So, and then we'll move to the Gaussian and the grounded spline. So the Gaussian, again, we can incorporate this notion of field of view in the sensor, and the grounded spline, and they did comparable. The grounded spline will, and at the end, it did outperform the Gaussian, but yes. So in conclusion, the individual Choquet intervals did not improve with respect to the EMI sensor, which was dominant in this data set we had, but the fusions did improve with respect. So the compositions and the arithmetic combinations of Choquet intervals did. Some other things that happened were, like we found out that we needed to ground the splines in order to get good detections, and once we actually grounded it, did outperform the Gaussian, but then we'd have to ask the question of, is it worth the computational complexity and time to actually do this? So that's a consideration to make. But yeah, in our future work, we're going to see if we can resample and fuse simultaneously, and we also looked at the fusion of CA. So if we can actually learn the fusion. We published a paper in FuzzIEEE, and we proposed a genetic program to go through and learn these fusion strategies. And I'd just like to thank the Army Research Office and Night Vision for their support in this project. Any questions?